Okay, so hello everyone. We are back. We are doing our, we finished our first exam. If you're in 230, if you're in 232, then this is the first big thing. We're beginning to work on our next unit. We're starting a new chapter, and we're working on double integration, or otherwise known as multiple integration. So what exactly does this mean? So if you think about what calculus is all about, calculus is really addressing two major questions. The first of these questions is, what's the rate of change of some quantity as another quantity changes? In other words, that's the question about derivatives, rates of change, and things like that. But the other question it tries to address is, how do we geometrically describe strangely shaped objects? Well, for a two-variable function, we know how to do the first of these things in terms of finding these rates of change. We know how to do that. We're going to take partial derivatives, gradients, directional derivatives, and so on and so on. Optimization of multivariable functions is a major component of what we try to do. But now we're going to address the second question. If you have some surface that's over some region in the xy plane, we're going to call that region D, then what's the volume between that surface and the xy plane? How can we talk about that volume? How do we calculate that particular volume? And to answer this question, we're going to start with an easier problem, which is, okay, well, before we try to figure out how to figure out what that weird volume is, we're going to worry about the case where this region we're talking about the volume over, what if it's a rectangle? Simple as possible. And specifically, or generally perhaps, we're going to look at the rectangle R is the interval AB times the interval CD. Now, this is not a cross product. Despite the notation, this is not a cross product. This is just a Cartesian product of one interval. The points in X are going from A to B, and the points in Y are going from C to D. So it's a regular Cartesian set product. And we want to talk about this volume. We want to figure out how to describe the volume of this region underneath that surface. Okay, so to do that, we're going to begin just by approximating it, as simple as possible. So to approximate it, we're going to divide the interval AB into M, as in Mary, different subintervals of length delta x. So that's what we see over here. So we're dividing up the interval from A to B into M, as in Mary, different intervals. Each of those intervals has a length of delta x. We do the same thing to the interval from C to D. This interval from C to D gets subdivided into N, as in Nancy, intervals. Each of those is of length delta y. And what's that going to do? That's going to take our rectangle and it's going to break it up into even smaller rectangles, all of the same area. In particular, the area is what? Well, if you stare at that for a second, you'll see that in the horizontal direction, the horizontal piece here is of length delta x, and the vertical piece here is of length delta y. So the total area of this rectangle Rij is delta. We call it delta A, but what is that really? Really, that's the change in x, delta x, times delta y. That's really all that comes down to. Rij, by the way, is what we're going to use for our notation when we talk about that rectangle in the ith column and the jth row. So with that in mind, we'll continue. We'll look at how this unfolds. So what are we going to do? We're going to take a sample point in each of those rectangles. So each of these dots in that rectangle, that represents a particular sample point. And can I zoom into this? Is that possible? Yes, I can. So if I zoom in here, then what I see is this dot. That dot is given by, that dot is this. Now this dot over here is xij star, yij star. That's what that dot is. It's a sample point inside of that rectangle. Bring it back to the regular size. So that's all that is, and that's what our xij star, yij star is. It's a sample point inside of that rectangle. Now the volume of the solid between the surface and Rij, what do I mean by that? I'm talking about this pillar, right? There's this pillar over here that's going between this rectangle Rij up to the surface. That gives us this pillar. And I want to know approximately how large is that pillar. Well, that volume is approximately the area of the base times the height. The area of the base is delta A, of course, that's just the area of that rectangle, that's delta A. The height is the evaluation of the function evaluated at that sample point, which is approximately f of xij star, yij star. So the total volume is approximately, the volume of, not the total volume, but the volume of that pillar is approximately f xij star, yij star times delta A. That's just regular old base times height. That's all that is. So you can think about this as the height and the area as the base, area of the base. The total volume is approximately the sum of all these rectangles. So if you want to actually find an approximation of the total volume under this thing, you're just going to add up all of those rectangles together. But of course, that's just an approximation. That's barely a sketch of what this thing could actually look like. But we notice that that's what's called, well, look, it sort of looks kind of familiar, doesn't it? It's called a double Riemann sum, much like the Riemann sums we saw from Calc 1. And as the subdivisions of M and N get larger and larger, that approximation gets better and better. So we actually say that the volume is just the limit of this double Riemann sum as M and N are both simultaneously going to infinity. That's our definition of the double integral. The double integral of this function fxy over that rectangle in R2 is given by this formula. The double integral over R of f of xy dA is the limit as m and n go to infinity of the mnth Riemann sum. The mnth Riemann sum over this whole thing. Okay, so now what exactly does that mean? A double integral is basically the amount of stuff in the region. That's how I usually like to think about it. And if your function is positive, then, well, okay, that function is positive, you can think about that as some kind of a height. So because it's some kind of a height, you can think about this integral over R of fxy dA, that's just the volume of the surface. Now, a function is integrable if this limit exists. Or to put this another way, your function is integrable if it turns out that's the same thing as saying your function is integrable if the double integral of the absolute value is finite, and which is to say that for our purposes, the volume is finite. Now, something, by the way, that's worth noting is that that's just a piece of notation. To say that when we're talking about the double integral over R fxy dA, that's just notation. We're going to see how to actually calculate that to get a numerical answer, but all of that really means is the amount of stuff, or possibly the volume. And you allow the volume to be negative if this thing is dipping below the xy plane, but generally speaking, that's just volume. That's all that really means. And we'll look at how to actually explicitly calculate that in a little bit. But before we do, just to get used to thinking about what this thing actually is all about, what if we're looking at, and here's a concrete example, let's say that R, our rectangle, is the rectangle from -1 to 1 in the x direction, and times -2 to 2 in the y direction. And fxy is the function root 1 minus x squared. So what's the double integral? Well, if you think about this, the surface z equals root 1 minus x squared, what would that mean? That's the same thing as saying z squared equals 1 minus x squared. Or to put that another way, x squared plus z squared equals 1. That's just a cylinder. And in particular, it's a half cylinder. And the reason you know it's a half cylinder is because this function is positive. It's only talking about the top half of this thing. So the integral, it's the volume of this upper half cylinder. So what would that be? Well, the area of this side here, the area of this half piece, what would that be? The radius is 1. The radius is 1, so that area would be 1/2 pi r squared, well, r is 1, so that's just 1/2 pi, times the length of this thing, and the length of this thing, we can see, is going to be 4. So the length times the area of the side or the area of the end of this thing is 4 times 1/2 pi, or in other words, 2 pi. That's it. That's the answer. That's your double integral for this guy. Okay. But that's a relatively simple example. In general, we're going to be looking at some much more interesting kinds of surfaces and different more interesting kinds of functions. So how do we actually calculate this thing? Well, think back to what our Riemann sum definition is. Well, if we're choosing the right sample points, you can write this a little more creatively. You can, for example, split up. Notice that this is the limit as m and n are both going to infinity, but you can split that up into the limit of m going to infinity, as in Mary, of the limit of n going to infinity, n as in Nancy. And if you do that, and you do it very carefully, you can bring in that limit into the first sum, giving us this lower expression that we see over here. So what have we done? All that we've done here is we've taken this limit, broken it up, and brought the limit as n as in Nancy goes to infinity inside the first sum. And that allows us to look at just this inner sum, this inner limit, this inner Riemann sum first. And indeed, if you look at that inner Riemann sum first, well, like I said, that's just a Riemann sum. And it's the Riemann sum as the subdivisions of y are getting smaller and smaller and smaller. Now, this is kind of cheating. I'm hand-waving a little bit because I'm kind of playing fast and loose with limits and sample points and things like that. But basically what's going on is, what if you just evaluate that inner limit first? And you're going to get a new integral, an actual definite integral from c to d in this case, because it's the subdivisions of y. Y is going from c to d. So you get a new integral, but that's just another Riemann sum itself. And in particular, this, if y is being integrated, then what we have over here, that is a function of x. And since it's a function of x, that's just a Riemann sum itself. So you can do the whole Riemann sum thing again, this time integrating from a to b, as the x divisions are getting smaller and smaller. So you end up with what's called an iterated integral. So this double integral over r of f x y dA is the iterated integral from a to b of the integral from c to d of fxy dy dx. That's all that this thing is telling you. So we should do an actual concrete example of this so we can see how to actually calculate one of these things. Now, this looks very scary, but in fact, it's actually quite straightforward. All that we're really doing here is integrating the inside first and then outside. So you integrate from the inside out. So you leave the out where it is. So let's take the integral from 0 to 3 of the integral from 1 to 2 of x squared y dy dx. Now, because dy is on the inside, you're going to integrate this y term first. And because we're integrating that first, that's going to become the integral from 0 to 3 of x squared y squared over 2. Because x squared, now as you anti-differentiate, whatever variable you're not anti-differentiating, just like differentiation, that's constant. So in this case, x squared, you leave that where it is. On the other hand, y squared, well, that's going to become y squared because you just have that y term there, and it's y squared over 2. Now, you're going to need to evaluate this from y equals 1 to y equals 2. Little pro tip, by the way, as you're doing these integrations, and I'm going to do this throughout all these examples, while you're doing these, we're now working with several different variables. So it's a really good idea to denote, what your what variables you're evaluating at if there's any ambiguity and you've got more than one variable. So I'm writing y equals 1 to y equals 2 to remind myself, aha, I'm really paying attention to the y terms in this case. So you evaluate that, still integral from 0 to 3 of y equals 2. So that's going to become 4y squared over, so 4x squared over 2, or in other words, 2x squared minus, now it's 1, so it's minus 1/2 x squared dx. We'll do that again. That's going to be the integral from 0 to 3 of, so 4/3 minus 1, so 4/2 minus 1/2, so that's 3/2 x squared dx. Or in other words, In other words, that's going to become 1/2 x cubed from x equals 0 to x equals 3, which is just going to be 27 over 2. There's your answer. Now, what if you did it in the other direction? If you're integrating with respect to x first, if x is on the inside, if that's your strategy, which is fine, you can do that. Integral from 1 to 2, integral from 0 to 3. In this case, that's going to become 1/3 x cubed y integrated from x equals 0 to x equals 3 dy. In other words, that's going to become the integral from 1 to 2 of 9y dy, or in other words, 9/2 y squared integrated from y equals 1 to y equals 2. Now that's, in other words, that's going to become 4 minus 1. So 9/2 times 4 minus 1, or 9 times 3 over 2, or in other words, 27 over 2. Aha! Now that's interesting. They're the same number. Isn't that strange? So they're the same number, even though you've integrated them in opposite directions. Now, if you're really thinking carefully about what's going on here, you should think to yourself, well, yeah, of course that should be the case. And why should that of course be the case? That should of course be the case because what is this? This is volume. We are at this moment trying to find the volume in this rectangle. This is the rectangle, by the way. Here I am. This, by the way, is the rectangle. This is the rectangle from 0 to 3 in the x direction times the interval from 1 to 2 in the y direction inside of R2. Now, if you think about that, well, of course that should be the same because this is a volume, and it shouldn't matter which direction you're integrating it with respect to. Of course. Of course. However, that's not always the case, and it happens to be the case because the volume is finite. In other words, the volume is well defined. And for most reasonable functions, that will be true. So this is what's known as Fubini's theorem. Fubini's theorem is sort of like an integral variant on Clairaut's theorem, which involved the exchanging of orders of differentiation. So what this is saying, in other words, is if you've got some integrable function over this rectangle, then that integral is just the iterated integral of that function in either order. You can do it in either order, provided that the volume is finite to begin with. And when I say volume, what I really mean is absolute volume. That is the volume taking your surface to be the absolute value. That is, you need this function to, in fact, be integrable. And if it's integrable, then you get this very nice result. And this result is called Fubini's theorem. Now, I'm not going to prove that, even though it seems obvious, that it turns out that proving Fubini's theorem is a colossally difficult task, but I'll give you the basic idea. It's like I said before, if you think about this double integral as a Riemann sum, you go through it, again, kind of playing fast and loose with how you're defining limits, but which is why I put that equal sign in quotes there, because you're kind of playing a little bit, it's a little bit tricksy doing that, but that's its own integral, and then the outside is its own integral, but you should in principle be able to do that in either order. That shouldn't matter. And because the order that you do it in doesn't matter, that's what basically gives us Fubini's theorem. Now that's not a proof, but it's sort of an intuition for, yeah, that should be true. It shouldn't matter what order we do it in order to find out what that volume is. So let's do an example of this. So for this example, what we're going to do is, because we're working in the rectangle from 0 to 2 times 1 to 2, that means that we've got x going between 0 and 2, and y going between 1 and 2. So this double integral over R of x minus 3y squared dA, let's say that we want to integrate it with respect to, I don't know, y first for no particular reason. If we do it with respect to y first, the outside integral is going to have the x bounds, the inside integral is going to have the y bounds. You can do this in either order. I'm just choosing to do it in the y order. So x minus 3y squared dy dx. So you integrate the inside first, and what's that going to become? Well, you integrate with respect to y, that's going to become xy minus y cubed, integrated from y equals 1 to y equals 2 dx. That's going to become the integral from 0 to 2 of, now plugging in y equals 2 first, that's 2x minus 8 minus x minus 1 dx. Actually, no, it would be minus x plus 1, wouldn't it? Yes. So, so that is going to become the integral from 0 to 2 of x minus 7 dx. In other words, that's going to become 1/2 x squared minus 7x integrated from 0 to 2, or in other words, 1/2 times 4 minus 14, or in other words, so if it's 1/2 4 minus 14, that's going to become negative 12. All right. Now, I didn't have to do it this way. You can do it in the opposite direction as well, and it'll give you the exact same thing. You can write this as the integral from 1 to 2, integral 0 to 2 of x minus 3y squared dA. And what would that be? Integral from 1 to 2 of, oh, sorry. One thing I really shouldn't do is write dA in that case, because it's not clear which direction is which. So that would be dx dy. So you're integrating with respect to x first. Integral from 1 to 2 of 1/2 x squared minus 3x y squared from 0 to 2. Integral from 1 to 2 of plugging in 2 in for all of this stuff. That's going to give us 2 minus 6y squared, which is going to become 2y minus 2y cubed from y equals 1 to 2, which is 4 minus 16 minus 2 plus 2, or in other words, once again, negative 12. Same exact answer as we would expect and as we would hope. Okay. So what if you have the double integral y sine xy? What are we going to do in this case? Well, in this case, what's going to happen, it's pretty much the exact same thing, but here it matters a little bit more which order we do it in. So, so let's suppose that we're going to do this with respect to x first. With the x first approach, this becomes the integral from 0 to pi, integral from 1 to 2, y sine xy dx dy. Now, if you integrate that with respect to x, that's going to become the integral from 0 to pi of negative cosine xy integrated from x equals 1 to x equals 2 dy. Which, in other words, is the integral from 0 to pi of cosine y minus cosine of 2y dy. And what would that be? Well, again, going through the motions, this is sine of y minus 1/2 sine 2y This is evaluated from y equals 0 to y equals pi. And in both cases, this is going to come out to 0. Well, that wasn't that hard, but what if we tried doing y first? Y first, this would become integral from 1 to 2, integral from 0 to pi of y sine xy dy dx. Now that you would have to do by parts. In this case, you've got one function of y times another function of y. So you'd have to integrate this by parts. And while you can do that and it's not terrible, it's going to be a little trickier and more frustrating than just doing it with the simple u substitution. So in this case, it's much better to do this with y first. Okay, so let's keep going. Now, here's another problem. What if you want to find the volume of the solid that's bounded by this surface, x squared plus 2y squared plus z equals 16, the planes x equals 2 and y equals 2, and the 3 coordinate planes. So 3 coordinate planes means means the xy plane, xz plane, and yz plane. So the 3 coordinate planes basically correspond to z equals 0, x equals 0, and y equals 0. Now, what that actually means is we're working with x is going to be between 0 and 2 because it's bounded by this plane y, x equals 2. And y is the same way. Y is also going to be bounded between 0 and 2. And what about z? Well, if you think about this surface is z equals 16 minus x squared plus 2y squared. So if x and y are between 0 and 2, that's always going to be positive numbers. And the smallest thing z can be is 0. So z is going to be between 0 and 16 minus x squared minus 2y squared. Okay, so the volume, in other words, is the integral from 0 to 2 of the integral from 0 to 2 of 16 minus x squared minus 2y squared dy dx. I could have written dx dy. It really doesn't matter. You can do this in the exact same way either way. So if we do it in this way, what's this going to come down to? That is going to be the integral from 0 to 2 of, in this case, let's say that we're doing it with respect to y first, 16y minus x squared y minus 2/3 y cubed, evaluated from y equals 0 to y equals 2 dx. And that is the, and if you just evaluate that directly, integral from 0 to 2 of 16 times 2, so that's 32, minus 2x squared minus 16/3, right? Because it's going to be y cubed is, well, that's going to come out to be, 8 times 2/3 or negative 16/3 dx. Following that through, integral from 0 to 2. 32 times 3 is 96. 96 minus 16 is 80, so that's going to be 80/3 minus 2x squared dx. So that's going to be 80/3 x minus 2/3 x, x cubed, evaluated from x equals 0 to x equals 2, which is going to be 160/3 minus, again, 16/3, which comes out to 144/3. 144/3, or in other words, 1 second. or in other words, 48. So that's our answer. The volume of this object is 48. Okay, so that's that story. Now there are some special tricks we can use. For example, some functions are what are called separable, which means they can be written as the product of two single variable functions. Now, this is handy because what this means is that, well, let's think about what happens with the iterated integral. Let's say that you have fxy equals gx times hy. Well, if you integrate gx hy with respect to, say, y, then gx is constant because x is constant with respect to y. So you can factor that out as you would an ordinary integral. So in other words, what you can ultimately do is split it up as the product of two different integrals. Now you can only do this when the two functions are products of different variables. So let's do an example of this. Let's say that we're working with the function fxy equals sine x cosine y. Well, then if you integrate that as you would a separable function, that becomes the integral from 0 to pi over 2. Integral 0 to pi over 2. Sine x times cosine y dy dx. Now if you factor out the sine x, integral pi over 2 sine x, integral to 0 pi over 2 cosine y dy dx. But now notice that this term is constant with respect to x. So that can then become integral 0 to pi over 2 sine x dx, integral 0 pi over 2 cosine y dy. So ultimately what we end up getting is negative cosine x 0 to pi over 2 times sine of y integrated from 0 to pi over 2, which comes out to just be, well, cosine of pi over 2 is 0, cosine of 0 is 1, so it's 0 minus negative 1, times sine of pi over 2, which is 1. So the answer is just 1. So that's one way that you can make our lives a little bit easier doing this kind of thing. Okay. Now, Fubini's theorem seems obvious, but there are some kind of funny ways in which this can go wrong. So, in particular, if you have that your absolute value is not in fact finite. So, take for example this function fxy equals x squared plus y. There's a typo here I am now seeing. This should be x squared minus y squared over x squared plus y squared squared, and you integrate that over the rectangle from 0 to 1 times 0 to 1. Well, what happens in that case? Well, that would be the integral from 0 to 1, integral from 0 to 1 of x squared minus y squared over x squared plus y squared squared. Let's say we're going to do dy dx equals. Now, just as an aside, it turns out, and I'm not going to go through this whole thing, but I'll just give you the long and short of it. It turns out that if you take the derivative with respect to y, so if you take del y of, let's see if I'm doing this right, del y of y over x squared plus y squared, you end up with x squared minus y squared over x squared plus y squared squared. It should be squared over there. So it turns out that that's what that derivative is. So I'm not going to go through the whole derivation of that, but take my word for it. The point is, this comes out to the integral from 0 to 1 of y over x squared plus y squared integrated from y equals 0 to y equals 1 dx. In other words, that's integral from 0 to 1 of 1 over 1 plus x squared dx. Well, that's just arc cosine. Or sorry, excuse me, that's just arctan, right? That's going to be arctan of 1 minus arctan of 0. But that's just pi over 4. And so that direction, the integral becomes pi over 4. But now what if you're going to do the same thing, only this time you're going to do it in the opposite direction? Integral from 0 to 1, integral from 0 to 1 of the same exact function, x squared minus y squared over x squared plus y squared squared dx dy. What's that going to be? Well, sort of by the same token, again, just as an aside, you can take del x of, in this case, it would be x over x squared plus y squared. One sort of similar story, this is going to become y squared minus x squared over x squared plus y squared squared. So in other words, this becomes the integral from 0 to 1 of, now that's x squared minus y squared, this is y squared minus x squared, so it's going to be negative x over x squared plus y squared, integrated from x equals 0 to x equals 1 dy. Or in other words, negative integral from 0 to 1 of 1 over 1 plus y squared dy. And if you do that integral, what are you going to get? Well, it's the same exact thing, only in this case it's going to be negative arctan 1 plus arctan 0, not that the arctan 0 matters, that's going to be 0, which is negative pi over 4. So wait a second, on the one hand you've got that this volume is pi over 4, but at the same time you're also told that this is negative pi over 4, even though you're integrating the exact same thing. What the heck's going on? What's going on is that this function isn't integrable. The problem is that this function blows up in either the positive or negative direction at 0, and you can't control that. So even though you get this nice thing called Fubini's theorem, which works in most cases, this is how it can break down. You can get different results for certain, not even that crazy functions. So it's weird. So you got to be careful when you're using this and making sure that your function is integrable. But in pretty much everything that we'll do in this class, it will be. So you won't have to worry too much about that. I just think that this is really weird and kind of cool. So there you go. Okay. Okay, so now suppose we have a non-rectangular subset. So this is a little more interesting. We've covered how to take care of rectangles and what happens with surfaces over rectangles, but what if you're dealing with a non-rectangular region? This is a little more general, a little more interesting in a lot of ways. Can you still talk about the volume under that surface? Well, of course you can talk about the volume, but how do you actually calculate it? Well, we're going to define a new function. And this new function we're going to define is defined over a rectangle that contains this region. So here's the way the function works. The function is our original integrand, fxy, if your point is in the domain. But if it's not, we're going to declare that this is 0. So on the left here, you have what the graph of f is. But on the right, you have the graph of our new function. And the only difference is that outside of this domain, outside of this region D, the value of the function is 0. So if R is a rectangle that contains this domain, we're going to define this integral like so. So, and you notice, by the way, that this is a perfectly reasonable thing to do because underneath that area, underneath this part of the graph that's 0, there's no volume. The volume of the actual solid in both these cases is the exact same thing. There's no volume under the 0 portion of it. So that's a reasonable definition, and then you're going to apply the same exact kind of reasoning as before. Now we're going to classify two different kinds of regions. One is going to be called type 1, and the other is going to be called type 2. And a type 1 region is a region that you can define between two curves that are functions of x, like this sort of teardrop looking thing on the left. That's a type 1 region because g1 and g2 are functions that define the top and bottom curve, and those are functions of x. A type 2 region will be the same thing, but rotated 90 degrees. This is a function. This is a region that's between two curves that are functions of y. like this kind of wobbly looking thing on the right, that is for our purposes, that's going to be a type 2 region. So that's what we're going to do this classification with. So let's say that we're working with the type 1. Type 2 is pretty much the exact same line of reasoning, so we'll just work with type 1 for now. So let's say that we've got our region, and it's between these two curves. That's a type 1 region, and our rectangle is a rectangle containing this, this region D, i.e. you've got that, that C, these lower and upper bounds C and D. C is always less than G1, which is always less than G2, which is always less than D. So this is the same kind of figure that we have underneath D. This is just a declaration so that this rectangle contains the region that we're interested in. And define our function big F xy is little f xy on D, but 0 outside of it. Well, by Fubini's theorem, we can just, with our definition, we can just do the iterated integral. Now, we're going to do y first, and that's a very deliberate decision. We're going to integrate with respect to y first. And the reason why we're going to do that is for a fixed value of x, your fxy is going to be 0 if your y is less than g1 of x. That is, if your y is outside of this, so in other words, we're looking at this kind of situation where you've got a y that's outside, so if this is our rectangle, right? So if you've got a y that's out, so if here's for a fixed value of x, if your y, oh, sorry, that's not what I wanted. If your y is outside, then you're equal to 0, but if you're inside, so out here, you've got big F xy is 0 for y less than or equal to g1 of x. But inside, you've got fxy is equal to little f xy for y between g1 of x and g2 of x. So that's the situation that we're working in, and that's what we're going to treat this thing as. So just to make that obvious. So in other words, since f of x, y is 0 when you're outside of g1, well, you can just ignore those entirely because that bit is going to be 0. The limits, in other words, become g1x, g2x. But now you're actually inside D, and when you're inside D, big F is equal to little f when you're actually inside D. So in other words, we get this kind of funny looking integral on the right-hand side where the limits of integration are actually variable. They're actually variable limits of integration depending on where you are in this region. The upshot of this is if you're dealing with the type 1 region, then this volume is just the integral from a to b of the integral from g1x to g2x fxy dy dx. Now, the same kind of reasoning will also show you how to do a type 2 region. The type 2 region is going to be the double integral, or rather the iterated integral from c to d of h1y to h2y of fxy dx dy. It's the exact same idea in this case. Now, let's do a concrete example of this. Let's suppose that we're dealing with the double integral of x plus 2y dA, and D is the region bounded by these two parabolas. The one is going to be y equals 2x squared, and the other is y equals 1 plus x. Now, I mentioned this when we were doing Lagrange multipliers, but it's even more important now. You have to draw the region. It's very important to draw the region so you really understand what this thing is that you're dealing with. In this case, you've got two parabolas. One of them is narrower but lower. The other one is a little wider but higher. That's the 1 plus x squared. And you can see that in this crescent-shaped thing. That's what's called a type 1 region because this region is between these two curves. The lower curve is y equals 2x squared. This lower curve, in other words, is going to be our g1 of x. The upper curve is going to be our g2 of x. And we're bounded between these values of 1 and -1 to give us this region D. So what do we have? We have, in other words, that that x is between -1 and 1, and y is between 2x squared and 1 plus x squared.
this is our region D. This is how we're actually going to define it. So when we actually do this integral, what's that going to be? Integral from -1 to 1, integral of 2x squared to 1 plus x squared of x plus 2y. dy dx. So we're integrating with respect to y first, because y is between 2x squared and 1 plus x squared. So as we're going through this, what's that going to become? Integral from -1 to 1 of, integrating with respect to y, that becomes xy plus y squared. Integrated from y equals 2x squared to y equals 1 plus x squared dx. Actually calculate that, integral from -1 to 1 of x times 1 plus x squared plus 1 plus x squared minus 2x cubed, because it's x times that thing, minus 4x to the 4th dx. You got to do some algebra to work out what this is going to be. So the algebra just will give you integral from -1 to 1 of x cubed plus x to the 4th plus 2x squared plus 1 minus 2x cubed minus 4x to the 4th dx. Integral from -1 to 1 of, now here I'm going to employ a little trick. So the trick that I'm going to use is, this is going to become integral from -1 to 1 of negative, in this case it would be -3x to the 4th, -3x to the 4th plus x cubed plus 2x squared plus x plus 1. And actually that should be a minus 2x cubed. It ends up not mattering, but that should be a minus 2x cubed. No, minus 2x squared, rather. Wait a minute. Whoopsie. I missed a couple signs. This should be a minus x cubed also, but again, it ends up not mattering. So there we go. I got the wrong sign. Okay, but I think that squares us off. So we should be good now. Dx, which is -3/5 x to the 5th minus 1/4 x to the 4th plus 2/3 x cubed plus 1/2 x squared plus x, evaluated from -1 to 1. And long and short, this is going to become negative, let's see if I'm doing this correctly, negative 6/5, I think, yeah, negative 6/5 plus 4/3 plus 2, after doing all that. And after just going through the calculations, I believe this comes out to 32/15. Now, there are a couple important notes that I should make as we're talking about these kinds of problems. First of all, integrals are scalars. Now, this is easy to remember if you just keep in mind that these integrals are really, at the end of the day, volumes. We're talking about volumes of different objects, of different strangely shaped objects. And in particular, sorry, I've got books that are falling. In particular, if you've got variables in the end, something probably went wrong. You shouldn't have variables because these are just simply volumes. That's the first point. The second point, which is related to this, is Fubini's theorem only directly applies to rectangles. if you try to change the order of integration, then you can do that, but you have to do that very carefully. You can't just do that directly like you do with Fubini's theorem, because again, if you were to do that, then once you finish that process, you're going to end up with variables in your final answer, and that's not going to get you what you want to do. Related to that, again, is the separability trick, the separation trick for rectangles. That only works for rectangles. If you've got a separable function, you can't separate it unless your region is rectangular. Otherwise, again, you're going to get variables in your final answer, and that is not good. That's not going to get you what you want. So all of these things are just, you know, ways of saying, hey, make sure that you don't have variables in your final answer. So let's look at an example. So what if you want to find the volume of the solid between the paraboloid z equals x squared plus y squared and the region D in the xy plane bounded by the curves y equals 2x and y equals x squared. So here's the region. It's drawn on the left-hand side. It's this little sliver. Now you can treat it as a type 1 region with g1 equals x squared and g2 equals 2x. That's between these two curves. So we've got, so where do they intersect? Well, they intersect when x squared equals 2x, and that's going to happen when either x is 0 or x is 2. So our x range is from 0 to 2. Meanwhile, so we've got x going from 0 to 2, and meanwhile we also have y going from x squared to 2x. So it's the double integral over d of x squared plus y squared dA, which is the integral from 0 to 2, integral from x squared to 2x, x squared plus y squared, dy dx, which comes out to integral from 0 to 2 of x squared y plus 1/3 y cubed from y equals x squared to y equals 2x dx. And yep, so it looks like I did that correctly. So if you do that, then then what does that give us? Well, after plugging those in, integral from 0 to 2, y equals 2x. So that's going to become 2x cubed plus 8/3 x cubed minus x to the 4th minus 1/3 x to the 6th dx. Okay, so that's going to become 1/2 x to the 4th plus 2/3 x to the 4th minus 1/5 x to the 5th minus 7/3, oh, sorry, not 7/3, minus 1/21 x to the 7th, evaluated from 0 to 2. Which is going to become, so if you plug 2 into all of this, that's going to give you 16/2, so 8 plus 16, 32/3 minus 32/5 minus now x to the 7th. What is that? That, I believe, is 128 over 21. In total, that's going to come out to 216 over 35. Okay, so that's great. Now, we can also do this, by the way, we can also do this as a type 2 region, but you got to be a little bit careful here. So we notice that on the left-hand side, we've got the curve h1y is 1/2 y, right? Because that's x equals 1/2 y. So this curve on the left-hand side was y equals 2x, but that's the same thing as saying x equals 1/2 y. Meanwhile, y equals x squared implies that x is root y in this case. So you can also write this as the double integral over d x squared plus y squared dA. Could also, so this is how you change the order of integration. You have to also change what the bounds are in this case. 0 to 4, integral from, now the first thing that happens, the bounds on y is between 0 and 4, but that means that x is between 1/2 y is less than or equal to x, which is less than or equal to root y. Since 1/2 y is less than or equal to x, that means that 1/2 y is on the bottom, the lower limit, and root y is the upper limit. X squared plus y squared dx dy. And that's going to be the integral from 0 to 4 of, and it's going to be the integral from 0 to 4 of 1/3 x cubed plus xy squared for x going from 1/2 y to x going to root y dy. Integral 0 to 4 of x equals 1 equals root y, so that becomes 1/3 y to the 3/2 plus y to the 5/2 minus 1/24, it's 24th y cubed minus 1/2 y cubed. I believe that I've done all that correctly. 3/2 and 1/2 plus 4. Yep. So unwinding all of this, this is going to become, this is going to give us 2 over 2/9 y to the, no, I'm sorry, not 2/9, 2/15 y to the 5/2 plus 2/5 y to the, no, not 2/5, I'm sorry, 2/7 y to the 7/2 minus 1/96 y to the 4th minus 1/8 y to the 4th. Evaluated from y equals 0 to y equals 4. And without going into too many details, once again, this becomes 216 over 35. So what does this tell us? Fubini's theorem does still apply in that you are allowed to switch the order of integration, but you have to do so very carefully. You can't just do it directly, you also have to change the bounds. So you can change the order of integration, but only if you change the bounds as well. And that's sort of the underlying challenge here. Okay. Now, how do you decide if a region is type 1 or type 2? Well, if you draw a single vertical line segment through the region, then, and every number, if you draw a vertical line segment through the region at any possible value x, and you stay within that region with a single vertical line segment, that's type 1. So think about this crescent here. But if you do it with a horizontal line segment, then that region is type 2. Now, in particular, this region is not type 2, because if you try doing that with one of these horizontal line segments, you're going to get 2 different segments, right? If you try doing that, you get 2 different segments while you do that with a single line. So because you get these 2 different line segments, this is not type 2. Because you get 2 different line segments here, that goes outside of the region. But the region on the right side, we said, is both type 1 and type 2 because you can draw a vertical line segment or a horizontal one. It will work in both cases. So you have to make a choice. Sometimes you'll have regions that are both type 1 and type 2, and you have to make a choice which one you're going to use. So part of the skill here is recognizing what the right choice is, or what the better choice is. Now let's suppose you've got this double integral. It's xy dA. D is the region bounded by the line y equals x minus 1, and the parabola y squared equals 2x plus 6. Now, the curves intersect when these are the same, right? You've got y squared is x minus 1, so x minus 1 squared is 2x plus 6. And if you do the algebra out, it turns out that that's going to happen at x equals -1 and x equals 5. So you can treat this either way. If you draw your vertical line segment, you'll find that it always is inside of this region. So it is a type 1 region, but if it's type 1, the top curve is this, the top curve, wait a second. The top curve is this guy up here, right? That's the top of this curve, and that is type 1. That is the top curve. You can think about that as this piece of the parabola. G2 is the square root of 2x plus 6. The bottom curve in this case, you can define the bottom curve as well, but the bottom curve is piecewise defined. So the bottom curve is negative root 2x plus 6 for values of x between -3 and -1. But at -1, at x equals -1, it changes to this line and becomes y equals x minus 1. So can you do this? Yes, but it's going to be a little annoying because of this sharp corner here. Let's see if we can make this a type 2 region instead. If it's a type 2 region, then you still got a left curve and a right curve. The left curve, in this case, is this parabola, which now is smooth. The left curve is going to be smooth in this case. The right curve, meanwhile, is this straight line segment. There are now no sharp corners in those different curves. So left curve becomes h1y is 1/2 y squared minus 3, and the right curve is y plus 1. In this case, you have y going from -2 to 4. And again, you can work out what the algebra is by looking at the curves at the points of intersection. Now, the curves are easier to work with for type 2, so we're going to treat D as a type 2 region. D is the points xy that are going from y is going from -2 to 4, and x is going from 1/2 y squared minus 3 to y plus 1. So now we can work out what our function is. Now, again, just to remind everyone, we're working with the double integral over d of the function xy dA, which is the integral from. Now we're treating this as a type 2 region, which means we're going to integrate with respect to x first. So it's going from -2 to 4. Integral from, now the lower bound for x is 1/2 y squared minus 3. The upper bound is y plus 1. And this is going to be xy dx dy. Integral -2 to 4 of 1/2 x squared y. Again, you've got x going from 1/2 y squared minus 3 to x equals y plus 1 dy. Doing that out is going to give us the integral from -2 to 4 once again of 1/2 y plus 1 squared times y minus 1/2 y squared minus 3 squared times y. All of this dy. And again, once you do all that algebra out, it's a little annoying, but it's not terrible. This becomes 1/2 integral from -2 to 4 of negative y to the 5th over 4 plus 4y cubed plus 2y squared minus 8y dy. which is going to become, so now that you've done that, you just anti-differentiate the whole thing. 1/2 times negative y to the 6th over 24 plus y to the 4th plus 2 y cubed over 3 minus 4y squared, evaluated from -2 to 4. And after you plug in all the numbers, that becomes 36. So that's your final answer. Now, can you do this as a type 1? Are you allowed to do so? Yeah, you are. That's possible. But if you look back for a second at our original problem, that's going to mean that your G1 is piecewise defined. You're going to have to do 2 different integrals in that case, 2 different iterated integrals. And that's going to be a little more work. And you're going to have to deal with some kind of weird square root business. So algebraically and geometrically, this is, the type 2 approach is far superior. So here's another example that we can look at. What if we want to find the volume of this solid tetrahedron bounded by these planes? Now, and the planes in question are x plus 2y plus z equals 2, the kind of interesting plane out of these. X equals 2y, x equals 0, and z equals 0. Now, the important observation here is that x equals 2y and x equals 0, those planes don't depend on z. X equals 0, well, that's just simply the yz plane. But x equals 2y, that's a vertical plane because it doesn't depend on z. So figuring out what the intersection is with the xy plane, that's not terribly difficult. That, we can see how that would work. Meanwhile, we can see that the interesting plane can be rewritten as the function z equals 2 minus x minus 2y. Now, that's above the xy plane for certain values of xy, but the question is which ones. In other words, where is this going to intersect the xy plane? We want to figure out what region this is above in the xy plane. Well, that plane intersects the plane x plus 2y plus z intersects the xy plane when z is 0, or in other words, x plus 2y equals 2. Or in other words, y equals 1/2 of 1 minus x. So it's bounded by the lines x equals 0, x equals 2y, and x plus 2y equals 2. So those are the 3 lines that, so those are these 3 lines in particular. So we've got one back here, that's x equals 0. We've got x equals 2y, and we have x plus 2y equals 2. That's where these 3 planes are coming in. That's where they're going to intersect. Okay, so this is the actual image of D. This is the actual figure of this region that this tetrahedron is sitting on top of. So after drawing this region that's bounded by these lines, then you can express D as either type 1 or type 2, but type 1 is going to be better because type 2 is going, you see if you do it as type 2, you're going to get this sharp corner on the right-hand side. So it's better to do it as type 1 in this case. So x is between 0 and 1, and y is between 1/2 x and 1 minus 1/2 x. So the tetrahedron is between these lines. You can now do this. We can actually find what the volume is by doing the double integral. Double integral over d of 2 minus x minus 2y dA. That's the same thing as the integral from 0 to 1. Integral from 1/2, oh, sorry, my mistake. 1/2 x, 1 minus 1/2 x, 2 minus x minus 2y dy dx. Going through this, integral from 0 to 1 of, now differentiating this with respect to y is going to give us 2y minus xy minus y squared from y equals 1 half x to y equals 1 minus 1 half x dx. It'll go from 0 to 1 to, and after just, I'm skipping ahead a little bit, but just doing all of the algebra to figure out what that is, that's going to eventually, okay, I'll do the first step. That's 2, 1 minus 1, just to be clear, as clear as possible, x times 1 minus 1 half x minus 1 minus 1 half x squared minus, in this case, minus 2 times 1 half x, so minus x plus 1 half x squared plus 1/4 x squared dx. And after doing the algebra, simplifying all that out, that's going to be x squared minus 2x plus 1. After working out all of the algebra. And I leave the details out to you guys to work out on your own, I trust you. But that ultimately becomes x cubed over 3 minus x squared plus x, evaluated from x equals 0 to x equals 1, which is just 1/3. That's the total volume of this tetrahedron. Okay, so now we've seen that. Now I want to do one more example because this one's quite important. So what if we want to evaluate this iterated integral, the integral from 0 to 1 of the integral from x to 1 of sine of y squared dy dx? Here's the problem. If you try doing that directly, the integral of sine of y squared dy, that doesn't have a nice antiderivative. That's a monster of an antiderivative to work out. It looks innocent, but it's really friggin' hard, basically impossible. So because of that, you're not going to be able to just do that in a nice way. So so what we're going to try to do instead, sine of y squared is really hard to antidifferentiate with respect to y, but very easy to antidifferentiate with respect to x. I mean, heck, with respect to x, that's a constant. So can we switch the order of integration? And here's what we're going to do. We're going to look at our bounds and look at the order of integration that we're given. What this tells us is our region D in question, it's going to be all x and y, so that, what do you know about x? Well, dx is going from 0 to 1, so that tells us that x is between 0 and 1, that's fine. And similarly, y is between x and 1. What does that look like? If you actually sketch that out, x is going from 0 to 1. That's not a problem. Y is going from x to 1. So what's y equals x? Y equals x. Well, that's just your basic diagonal line. And y is bigger than x, but less than 1. So y is above x, but less than 1. So here's our region D. That's the region D that we're going to be integrating over. So with that in mind, how can we do this? Okay, well, we see that this is y equals x, but if we want to rewrite this in terms of y first, well, that's just x and y. What's y between? Y is going to be between 0 and 1. We can see that y is between 0 and 1 in this case. And what about x? X is going to be between 0. So the smallest thing that x can be is 0. Oops. But the largest thing that x can be is y on the other side. So x is going to be between 0 and y. So the integral from 0 to 1 of the integral from x to 1 of sine y squared dy dx, we can take this from an impossible integral to a much easier integral, integrating from 0 to 1 for y and 0 to y for x. So we're putting x first. The integrand doesn't change because we're not changing the integrand. We're only changing the way we're expressing the region that we're integrating over. So dx dy, keep on going, integral from 0 to 1 of x times sine y squared, integrated from x equals 0 to x equals y dy. That's the integral from 0 to 1 of y times sine of y squared dy. So y sine of y squared dy. Now, how are we going to do that? Well, that's a much easier integral to do, right? That's just a basic u substitution. So how's that going to work? Well, it's just about as simple as you could really want it to be. That's negative 1/2 of cosine y squared evaluated from y equals 0 to y equals 1. Which is just, now you plug in y equals 1 into that and y equals 0 into that, that's just 1/2 minus 1/2 cosine of 1. Cosine of 1, that's about the best you can really do there. So that's our final answer. So now that's a very simple integral to do once you change the order. So that's how Fubini's theorem works in this context. Can you change the order of integration? Yes, and you should a lot of the time. But when you do that, you have to be very careful with how. You have to be very careful with how you do that by making sure that your bounds still work out and you're still describing the region you want to describe in a way that's not going to give you variables in the end. Because again, you cannot have variables in the end. The variables in the end means something has gone wrong. These are basically volumes or quantities of stuff, and you shouldn't have any variables at the end there. All right, so a couple important properties, and these are basic things that that shouldn't really be too shocking. So double integration is linear, which means that you can add functions together and just take the double integrals of each piece. It's also scalar multiplicative, which means that you can multiply some function by some constant and just pull the constant out. That's not going to do anything unusual. It's just like regular integration in that way. In fact, these properties come from regular integration once you think about iterated integrals. And another simple and intuitive idea is if you have two different regions, D1 and D2, and you combine them, you take their union, and they don't overlap, except possibly on their boundaries, which is fine because that volume is 0. But if that's the case, then you can just add them as you ordinarily would. That's not a problem. The last one that I want to point out is this question of area. So it turns out, what happens when you take the double integral of the constant function 1? Well, that's just a block. That's just measuring the volume of a block with a height of 1 and an area and a base of area d. And the volume is the area base times the height. But the height is 1, so that's just the area of the base. So it turns out that if you take the double integral over a region d of the constant function 1, that's just the area. That's all that is. So for example, let's look back at our crescent from before. What's the area of that thing? Can we find out what the area of that strange object is? Yeah, we can now. Let's see if we can work that out. That's just the constant function 1, which is often just written as there being nothing there at all. Integral from -2 to 4 of y plus 1 minus 1/2 y squared plus 3 dy. Or in other words, actually, I'll write that further back, dy. Or in other words, integral from -2 to 4 of -1/2 y squared plus y plus 4 dy, or in other words, -1/6 y cubed plus 1/2 y squared plus 4y, evaluated from -2 to 4. And if you do all of that calculation out, the answer is just going to become 18. So that's the actual area of that crescent shape. Sort of crescent, not really, but anyways, you get what I mean. All right, so we'll continue this discussion tomorrow, and we'll start talking about polar coordinates, and we'll begin looking at other ways of looking at strange volumes under other kinds of surfaces and different tools that we can use to do that. By the way, just as an aside, most of the next few lectures, in fact, of pretty much everything that we do going forward, is all about integration. So if you're feeling a little rusty on your integration techniques, especially U substitution and integration by parts, if you're feeling rusty on integration by parts and U sub, then take some time to do some examples of those on your own, because those are really important. And you are almost definitely, you are definitely going to see those at different points this semester. So make sure you take some time to review those if you're having a little trouble with that. And if you want extra help, then let us know, and we'll have some special examples of that during either recitation or guided study group. All right, thank you everyone, and we will talk to you later on.